Okay, so I'm going to do now an example of doing a triple integral using cylindrical coordinates. And the problem is the following. So we want to find a triple integral. We're just going to integrate the variable z. So we're integrating z over a region. Remember that for triple integrals, the regions are already 3D things in space. So in this case, it's definitely impossible to try to do the graph of the function. So we're going to integrate this function on this volumetric region. So what is this region? Well, the idea is that you have a cone which is given by this equation. Usually I'll at least tell you the name of the surface, so that you know that this, for example, is like a cone, and so that way you imagine what it should look like. And so here's a cone, right? As you can see, the point is that this cone really keeps growing in size. So it's like an infinite cone. So in order to get like a finite region, which is because here we're not doing like things like improper integrals. In order to get like a finite region, you have to cut the cone by intersecting it with the plane. So this is what's going on here. The cone would have extended naturally. It would have kept going. But along the way, what we did is cap it off with this plane that's at height 1. Okay, and so that gives you a finite region. And the idea is that we want to use cylindrical coordinates basically because, well, an expression like x squared plus y squared is something we would have studied with polar coordinates. But now, since we are in 3D space, now we have to keep track of the z coordinate. Okay, and so basically, that's what we are going to do. So let's see. The thing that I mentioned last time. Right. So again, when you do cylindrical coordinates, let me write it here somewhere. The change of variables. X becomes r cosine of theta, y becomes r sine of theta, and z becomes c. That one does not change. So in this case, the important thing is that the volume, the volume, let me write it here. Let's put it here. The volume element is the same volume element as in polar coordinates. I mean, it's the same as the area element in polar coordinates, which was r dr d theta. Okay, but then you have to multiply this by the dz factor, so you get dc, so you get r dz dr d theta. Okay, so let me just replace that here. And so what we have to do now is figure out what the bounds are. All the problems about triple integrals, once again, boil down to finding the correct bounds. So let's try to do that. So one more time, this goes from the inside to the outside. So in this case, we're going to do this integral first. And then we're going to do the one in the middle. And then we're going to do the last one. Okay? Now, there are different ways to see this, to see the bounds. basically what you're going to do, I'll add a video so that it's a little bit more clear. But so again, this was the cone, right? The point of the cone is that it has a symmetry, right? If you rotate about the cone, like you all the side, all from all directions, it looks the same. Okay. So what that means is that sometimes the point is that finding the bounce from the 3D perspective is just a little bit too complicated. So you can imagine that you slice up this cone by passing a plane through it, okay? And when you slice it up, then you get something that looks more like a surface. So, and then so you will slice this up, and then the entire, by cutting it with the plane, and then the entire region itself of integration can be obtained by rotating this thing that you cut by an angle of 2 pi. So let me just try to explain this more precisely. Well, I'll show you first a video, and then I'll go back to this. So I'm going to explain to you how to find the bounds in cylindrical coordinates of the triple integral we were trying to do. Remember that we were looking at the cone given by the equation z equals root of x squared plus y squared. As I mentioned before, the point here is that this region extends indefinitely, which is what you see in the picture. So in order to work with a finite region in space, which is where the integration will take place, we take the plane z equals 1, which is this plane that you see here at height 1, and we intersect that with the cone. And so now the triple integral only takes place in the region between this plane and the cone. And so once you know that, we have to find the bounds in cylindrical coordinates. Basically, in many problems involving cylindrical coordinates, there's a symmetry that you can use, which just stems from the fact that none of the equations which define the region of integration actually involves the angle theta once you switch to cylindrical coordinates. So for example, z equals 1 does not involve the angle theta, and z equals x squared plus y squared, or root of that, does not involve theta, because once you switch to cylindrical coordinates, this just gives you z equals r. So visually, the fact that this does not involve cylindrical coordinates just means that as you rotate about the z-axis, you essentially see the same figure from all points of view. Okay, so in order to exploit this symmetry more conveniently, what you can do, let me just delete this plane for now. You can instead intersect this region with a different plane, and say, let's take the plane x equals 0. And by doing that, it doesn't really matter which plane, which vertical plane you choose. That's the whole point of the symmetry. But by doing that, what you see is something like analogous to the xy plane. Okay, so now there's like a reverse. You're switching the roles, and z becomes like y, and any of these axes on the floor becomes like the x-axis. Since it didn't matter which axis you're using downstairs, you can think of it as being like an r-axis. And so you have like the z plane, and here in this plane you get a region which looks more like a region that you would use for double integrals. So basically, you get this triangle that you see here, and then you have to find the bounds for that triangle, and in the same way in which you would have found them if you had used y and x coordinates. So that's what I'm about to do in the remaining part of the video. Okay, so here's the idea of what the video was saying. The point of the video was that this is a picture in 3D, but you only need to look at what's going on when you cut it with the plane. When you cut it with the plane, so this is a 3D version. So when you cut it with the plane, you get something which looks like this. Okay, and what I'm saying is that these bounds are easier to find just from this point of view. And so why is that the case? How can we find the bounds for the triple integral? Well, first we have to do this integral. We're integrating first with respect to z. So that means that r and theta are held constant. So imagine that you take r and theta to be constant. Well, basically, any of these planes are obtained by setting theta equal to a constant. So here, these planes are obtained by setting theta to constant. Okay, and so we already took care of that. If you want to think about it from this point of view, fixing the value of theta was like fixing one of these rays. Fixing the value of r is like fixing the point of the circumference, right? So you're looking at points that have a fixed value of theta and a fixed value of r, so something like this, and the only variable that's allowed to change is z. So these are like the vertical arrows that I was trying to do last time. When we cut the plane, we always think of this as the z-axis. What I'm saying here is that from this perspective, right, all the points from what you're doing from this point of view is just like fixing a distance r from the z-axis, right? Imagine again, when you take this fixed distance r and you rotate this by 2 pi, then this point gives you the circle that you cared about. So you're looking at the points with a fixed distance from the origin. And then the bounds for z are just obtained by drawing vertical arrows that are parallel to the z-axis. So you do something like this. So in other words, these are obtained, this uses vertical arrows again. So this is now very similar to like one of these non-rectangular regions in the plane. In fact, if you prefer, you're always free. You can always call the vertical axis the z-axis, okay? And you can call the remaining axis r, the r-axis, okay? So now, by doing that, you actually have a problem where this is playing the role of x, this is playing the role of y. but the bounds are something that we know how to find from before. So again, let me just draw this a little bit more carefully. So what is this line corresponding to? Well, that corresponded to the equation of the cone. The cone had equation z equals root of x squared plus y squared. When you change this into polar coordinates, this becomes c equals root of r squared. And so the equation of the cone here is just z equals r. Which is like the analog of y equals x, which is what you would expect from this perspective if you think of this as y and this as the x-axis, which I'm calling r for convenience. Okay, and so using using this order of integration, dc dr is like using dy dx, and that's why we're using vertical arrows to understand this region. And so notice that the arrows start at z equals r, and they end at c equals 1 because that was the top of the top height that we were allowing. And then again, the bounds for r are just the smallest and largest value that r can take. The smallest value r can take is 0, that's the distance from the z-axis. And the largest value that r can take is this distance from the z-axis, which is 1. So the bounds go from 0 to 1. And theta, because the problem was symmetric, you can just rotate by 2 pi. And so the angle for theta is just from 0 to 2 pi. So again, the point of you exploiting the symmetry is that you think of this as being some analogous problem to the one of dy dx order of integration. Okay. And so after you have done this, now this is an easy integral to do. We're integrating first with respect to, sorry, this should be r. We're integrating this first with respect to c, right? And so this is just r times c squared over 2 times, well, evaluated at c equals 1, c equals r times the r d theta. And so that gives you 0 to 2 pi, 0 to 1 r times, well, 1/2. One minus r squared, the r d theta. Okay. And I took the 1/2 outside the integral, so that gives you 1/2 integral from 0 to 2 pi. Now you're integrating r minus r cubed, the r d theta. And this is easy, this is 1/2. So this goes from 0 to 1. And this goes r squared over 2 minus r to the 4 over 4 times the theta. You're evaluating here where r equals 1, r equals 0. And so you end up with 1/2 times 1/4 minus, well, times the integral from 0 to 2 pi of 1/2 minus 1/4 the theta, and that's 1/4, so you get 1/2 times 1/4 times 2 pi, because there's nothing that depends here on theta, and so you get pi over 4. So this integral that I just did equals pi over 4. So next time, what I will do is explain spherical coordinates, and then I'll do an example with spherical coordinates, and then we'll do examples where you can use both cylindrical and spherical coordinates so you see the difference between them.